Hello, my name is Tilak and I'm affiliated to Spire Lab, IISc Bangalore. Here, I'll be presenting our work where we investigate the virtual lip trajectories during the production of bilabial stops and nasals at different speaking rates, slow, normal, and fast. This would be the flow of my presentation, and I will start with the introduction first. A complex interaction between upper and lower lip is often observed in a labial contact during bilabial stop and nasal production. This may be caused due to the tissue compression when the lips get in contact with each other to form a closure. So it becomes interesting to see how lips movement would behave if the upper lip and lower lip were not hindered by each other during a labial contact. This is the genesis of the concept of virtual lip trajectory. A virtual upper lip or a virtual lower lip, henceforth denoted as VUL and VLL respectively, was formally introduced by Lofquist and Draco. It is a hypothetical trajectory below in case of VUL and above in case of VLL, the measured upper lip and lower lip trajectory, respectively, which could have been achieved by the upper lip or the lower lip if the lips were not in contact with each other during the production of bilabial stops and nasals. We in this work propose a novel technique to estimate the virtual lips during the production of bilabial stops and nasals. Why only bilabial stops, that is p and b, and nasal, that is ma, were considered for this study? It is because these are the only sounds during which lips come in contact with each other, a condition that is required for the investigation of virtual upper lip and virtual lower lip. A subtle difference between bilabial stop and bilabial nasal is shown here in this figure, where the blocked air stream is released via mouth in case of bilabial stop, and for the bilabial nasal, the blocked air stream is released via nose. The goal for this study are as following: to estimate the virtual lip trajectory from the given upper lip and lower lip trajectory, and secondly, to analyze the characteristics of these estimated virtual lip trajectories at three different speaking rates: slow, normal, and fast. The motivation to carry out this investigation was: could these estimated virtual lips reveal specific articulatory planning during the bilabial stop and nasal production? Using the virtual trajectories, can the lip displacement pattern be analyzed? Could the features derived via virtual lips help in discriminating the speech rate? Moving to the next section, here I will briefly talk about the dataset used in this work. The articulatory movement were recorded using 3D electromagnetic articulograph AG501. A microphone was used for the simultaneous audio recording. 6 sensors were glued to the subject to obtain the 12 articulatory trajectories, both in X and Y direction of the mid-sagittal plane, as shown here. 10 subjects, 5 male and 5 female, of the age range 18 to 22 years participated for the data recording. All subjects were non-native speakers of English. The utterance was of the format Speak VCV Today, where every utterance was repeated thrice in each of the three different speaking rates, namely slow, normal, and fast. Total 9 utterances of one VCV sequence was recorded. The list of VCV stimuli had all 15 possible combinations of 3 consonants, namely B, B, M, and 5 vowels A, E, I, O, U, making a total of 450 recordings per consonant. The table below shows the duration of consonant for 3 different speaking rates. These values suggest subjects were able to modulate the speaking rate quite well. Few other details regarding the data are as following. Recordings of the lip movement were done at a sampling rate of 250 Hz in a mid-sagittal plane. The VCV boundaries were manually marked by a team of 4 annotators. The boundaries were marked by observing spectrogram, the raw waveform, and glottal pulses simultaneously using a MATLAB-based in-house annotation tool. This slide shows a screenshot of MATLAB-based annotation tool for marking VCV boundaries. Care was taken to discuss the ambiguous cases among the annotators before the boundaries are decided or finalized. This section deals with some key research questions that we address in this work. So the objectives were, firstly, to come up with the method to estimate VUL and VLL trajectory. Secondly, deriving some useful features from these virtual lip trajectories. Then, statistically analyze the virtual trajectory features across 3 different speaking rates. And finally, carry out a classification experiment to check whether the virtual lip features help in speech rate discrimination. I will discuss each of the objectives and then strike them off once completed. I will now discuss the first objective, that is the methodology to estimate the virtual lips. Before going any further, I will explain some terminologies used. Typically in a VCV sequence, we have a vowel region, a consonant region, and again a vowel following the consonant. But here we define the transition regions, which refer to the regions where lip initiate its transition from vowel to consonant to form a lip closure, denoted by VC transition region. And then it's transitioned back from consonant to the vowel, denoted by CV transition region. We approximated the transition regions as 1/3 of C regions in both sides of the C start and C end boundary. N1 is the start of VC transition region, N2 is the end of VC transition region. Similarly, N3 is the start of CV transition region and N4 is the end of CV transition region, as shown here by the markers. Including the transition region with the consonant region is what we refer to as the extended C region. Now, some of the assumptions which hold our formulation are as following. The upper lip and lower lip are approximately related by an affine function, as shown here, where alpha n and beta n are the slope and intercept respectively at a sampled index n. Relationship between the virtual upper lip and virtual lower lip in the entire extended C region is similar to that between the upper lip and lower lip in the transition region. We consider this because we observe in the transition region the relation between upper lip and lower lip movement is approximately linear, and this typical trend gets disrupted in the C region due to the contact between the lips. Therefore, we assume if there is no contact between the lips, the same linear relation would hold in the transition regions, and therefore we have the next assumption as the alphas and betas in the case of virtual upper lip and virtual lower lip varies linearly from VC transition region to CV transition region. Now, alpha n is the slope between the upper lip and lower lip computed locally using a small segment of trajectory. It is primarily negative in the VC and CV transition regions, as in the VC region, UL and LL are approaching towards each other, and in the CV region, they move away from each other. Whereas in the C region, alpha n is positive since the lips movement in the C region are coupled, that is, they get obstructed and move together. Therefore, we assume that a positive and negative value of alpha n indicates whether the lip are in sync or out of sync respectively. While the negative value of alpha n gradually becomes positive as lips come in contact with each other, we do not know exactly at what time instant it happens. We assume that the slope between virtual upper lip and virtual lower lip remains negative throughout the extended consonant region. Instead of considering only the regions with positive alpha n, we algorithmically find out which sample range, that is sample index M1 in a VC transition to M2 in CV transition, the slope between VUL and VLL differs from that between the UL and LL, assuming that it varies linearly in this range. The equation here provides an expression for linearly interpolated alpha n and beta n from M1 to M2, as shown here by the red line in this particular subplot. We pose the estimation of VUL and VLL as an optimization problem, where VUL could be approximated as an affine combination of estimated alphas and betas with estimated lower lip, where the estimated lower lip is where the virtual lower lip is estimated using equation 3. We use this particular objective function, that is equation 3, to estimate the virtual lower lip. This objective function ensures that the estimated virtual lower lip is smooth and low pass in nature, similar to a typical lower lip trajectory. Following constraints was implemented to the objective functions. VLL should lie above the given LL, and VUL should lie below the given UL, as per the definition of the virtual lip trajectory. The upper limit of the VLL is set to the maximum value of UL in the extended C region. Similarly, a lower limit on the VUL is set to the minimum value of the LL in the extended C region. The boundary constraints ensure the estimated VLL matches with the LL outside the estimated region. For every choice of M1 and M2, the optimal M1 and M2 was selected by running an optimization problem, optimization equation, that is equation 3, for all possible combinations of M1 and M2, and selecting the one which result in least objective function value. Now I will discuss the results and the remaining objectives. These plots show some samples of measured UL and LL trajectory and their corresponding derived virtual trajectory. One thing which is common in all the measured trajectory is some complex behavior taking place in the UL and LL trajectory, particularly in the consonant region, probably due to the tissue compression factor during the lip closure. And from these, we estimate the virtual UL and virtual LL trajectory. In example 1, N3, we can clearly see the lower lip pushing the upper lip in the upward direction, as seen here and here, due to which a dent is visible in the upper lip trajectory. Next to them are the estimated virtual lip trajectories VUL and VLL in magenta and cyan color respectively. These trajectories are smooth and show the unhindered movement of the lips. In example 1, there is an overlap of the virtual trajectories, which is not present in example 3. It may be because the range of LL in example 1 is much more than the range of LL in example 3. In example 2, the dent is not present, but one can clearly observe the measured UL trajectory got disrupted by the LL trajectory in the C region. Next to it is the smooth virtual lip trajectories derived using our formulation. Coming to the next objective, that is deriving the representation from the virtual lip trajectories. For this, let's dissect one of the plots from the previous slides. The features derived are as following: VULMD, that is the maximum deviation between the upper lip and the virtual upper lip, as shown here. VULMDL, the location of the maximum deviation. VULR, range of the virtual upper lip. Similarly, for VLL, features derived are VLLMD, VLLMDL, VLLMDR, VLLR. We now discuss the next objective, that is statistical analysis of the virtual lip trajectories at different speaking rates. Shown here are the bar plots of 6 proposed parameters computed at slow, normal, and fast rate using red, blue, and green bars, respectively, separately for P, B, and N. The error bar shows the standard deviation. A red star indicates the parameter in the respective case is significantly different between slow and fast rate. Here we see in the slow rate, the VULMD is significantly higher than VLLMD for P, B, and M. This is true for normal, but not for fast rate. This indicates that LL matches the VLL more closely than what UL does, as during the consonant segment, the UL and LL come in contact with each other and interact to deviate their trajectories from the respective VUL and VLL. It appears that LL exerts more pressure on the UL, causing UL to deviate more from its virtual target, similar to the finding of Lofquist et al. Next, here we observe a significant drop from slow to fast rate in VULR and VLLR, which suggests an increase in speaking rate. Secondly, the lips in the virtual motion has to reach its target at an instant within the consonant region, starting from its position in the vowel region and again returning back to the post-consonant vowel position, completing its virtual movement cycle. In the fast rate, VULR and VLLR become small as lips get less time to complete the movement cycle. Therefore, it comprises on the extent of the movement from its position during the vowel on either side of the consonant. However, at a slow rate, the planning of virtual lip movement could exploit the longer duration, which results in a relatively larger range for VUL and VLL. The VULR reduces compared to its slow counterpart, suggesting that a reduced VULR is probably a result of articulatory planning during the bilabial production at different rates. Now, coming to the fourth and the last objective. The derived virtual lip parameters separately as well as their various combinations from all 10 subjects are pooled and used as a feature in order to carry out speaking rate classification tasks using SVM classifier in F1 score as an evaluation metric. The table above shows the F1 score from slow to fast rate classification using the baseline feature and the proposed virtual lip trajectory features. As clear, MD features perform the best for the bilabial stops, and combining features improve F1 score, suggesting virtual lip features provide better discrimination compared to the baseline features. Now, concluding my work, virtual lip trajectories during bilabial stops vary significantly with speaking rates, resulting in F1 score of 0.8 for slow versus fast rate classification, which is pretty good. Future work includes removing the effect of jaw before estimating VUL and VLL, relaxing the linear relationship assumption, and carrying out the study in a vowel-specific manner. I would like to thank Shankar for his help with generating the figures, and a big shout out to Department of Science and Technology, Government of India for their support. With this, I end my presentation. For any queries, please write to us at spiralab.ee@iisc.ac.in. Thank you. I hope you enjoy the conference.